Hello everyone and welcome to the SimScale webinar. Today it is all about CAD simplifications and faster electronics design simulation with SimScale. I'm your host and moderator for today's session, Yusuf Murad, and I'm a product marketing engineer here at SimScale. It's really a pleasure to host this webinar today, and I can see so many attendees already in today's session. That's really exciting. And I would like to introduce you to one of our latest features to drastically reduce CAD preprocessing with two experts on my side today, namely Vuko Vukcevic and Alexander Fischer. Alex has a background in computational mechanics and control technology and worked for 10 years in different product and engineering roles, building a fully cloud and web-based simulation platform. He's a co-founder of SimScale and leads the company's efforts for thermal management and electronic solutions. I'm also very delighted to welcome our second speaker for today, namely my great colleague Vuko Vukcevic. Vuko got his PhD from the University of Zagreb, developing computational ship hydrodynamic CFD software with one of the two main authors of OpenFOAM. He currently leads the simulation team at SimScale, responsible for developing and integrating solutions. Just as a side note, at the end of this webinar, we will have time to cover all your questions in a dedicated 15-minute Q&A session. So please, if you have any questions about the webinar, today's demo, or SimScale in general, please put them in the chat or little Q&A box in our GoToWebinar tool, and we will make sure to take them one by one at the end. Okay, so today it's all about preparation and simplification of complex CAD models. These tasks can take away valuable time that might be spent on the design and optimization of electronics, cooling devices, and thermal management of systems. The electronics market is fast-growing and highly competitive, which forces engineers to close the gap from production-ready CAD to simulation-ready CAD in order to facilitate a productive design workflow. To overcome this bottleneck, we developed a new and robust solver that simplifies heat transfer calculations in complex assemblies and allows for simulation directly after importing your CAD model. The magic that's happening is that CAD parts are immersed in the background mesh, making the contacts and intersections of various parts resolved at the mesh level. This new feature allows engineers to spend less time on CAD preprocessing and more time focusing on design exploration and team productivity. So let me quickly introduce SimScale. So we see many engineers and designers today new to SimScale who are curious to learn what we are all about. So SimScale's mission is that we are committed to making engineering simulation more accessible, whether it's from thermal, structural, and fluid simulations to other industries who couldn't afford simulation so far. And we strive to introduce digital prototyping into any R&D cycle and throughout the whole R&D process. To summarize it, we are focused on delivering computational resources that scale up on demand. We offer streamlined simulation workflows and offer modern sharing and collaboration features. And we would like for engineers and designers to be able to simulate early, simulate more, and especially simulate now in one single SaaS application, helping you from the beginning to the end as a complete solution, basically, to facilitate short production life cycles and leverage SimScale for high optimization needs. Our mantra in one sentence: you come with your CAD model and leave with a design decision. It's really that simple. Okay, before I hand over to my colleague Alex, let me spend quickly a couple of minutes to talk to you how simulation will be used in the future. On this slide, you can see that the conceptual breakdown of the product lifecycle is going kind of the classical approach from the conceptual phase over to the manufacturing and production phase. And most simulation processes or designs are working, as you can see on the slide, which is admittedly quite a simplistic way to look at how simulation works, but I think it captures the status quo of most workflows quite accurately. And typically you have on-premise hardware rolled on an elaborate software IT stack, which costs you most often a fortune and also requires orchestration between different teams like engineers, IT support, and potentially other vendors to support you in your simulation journey. And that's quite complex. Note that this is on purpose put at this stage of the design cycle because it's actually like that in real life. So really late in the design process, actually, where you come up with a simulation tool. So basically, the if-then scenario looks as follows. So when you have a mature CAD geometry, then I'm basically using simulation. But of course, there's a lot more to that. Today, there's a lot more movement going from reactive design, talking about design validation, as you can see, to iterative design. So simulation actually driving the design. There's also a lot of other things such as generative engineering, the early stages up to predictive maintenance, and leveraging things like digital twins on the production side. So how is SimScale now approaching this? All the IT complexity is taken by us, SimScale, and also handled by us, whether it is data storage, node handling, and all the various bits and pieces you actually don't want to deal with as a designer or engineers. So we are taking care of this kind of orchestration and infrastructure. On top of that, we have integrated a lot of neat technology modules that are tightly integrated into the SimScale ecosystem, such as CAD editing, meshing, and a lot of other capabilities. So this ranges from structural mechanics use cases, thermal, and also CFD capabilities, and everything is packed into one single SaaS application, namely SimScale, which gives you access to all of these analysis types. So everything is also accessible via a standard graphical user interface, so GUI, and also accessible programmatically via a standard API using C# or Python. This is of course not all by us. There are a lot of third parties involved and also a few that leverage our API actually for apps and things like that. If you're interested in that, we are more than happy to share a few customer success stories with you. With that out of the way, I now hand over to my colleague Alexander Fischer, who introduces you to SimScale's approach versus traditional CAE.
Thank you, Yusuf, and welcome also from my side. I'll be happily sharing with you right now how we make simulation not just accessible by giving you hardware and software access to simulation, but also kind of supporting every engineer in his onboarding journey and also kind of allowing him to use simulation without having any productivity loss. We'll start off with essentially showing how this is right now done. Traditional CAE tools are already in heavy use. They are in use since 30 years and are actively developed since that time. But there is some drawback to it. Essentially, simulation is mainly used in the design cycle by simulation teams that take over once designers and engineers come up with a first concept, have most of the components defined, then hand it over, and then there is essentially a queue of simulation jobs or simulation tasks that are handed over to simulation experts. Once those are done, kind of the feedback loop starts, and the designers and engineers can start with a new iteration. That is quite costly in regards to time and also not really efficient and fast. You would have a big benefit of starting earlier and simulating earlier already in kind of a concept phase on sub-levels, etc. So while traditional simulation usage is very limited within the design process, we try to expand this. So that's where the SimScale Cloud Simulation Platform sits. We're trying to expand simulation usage to designers and engineers, but we are also expanding the way simulation experts can make use of their expertise by supporting designers and engineers in this workflow. That's also very interesting in the electronics field, because usually there's often mechanical engineers, there's electrical engineers, where their daily work has many different components, and simulation and testing setups or iterations in simulation would be just one part of their daily job. So kind of getting this support either by simulation experts or the SimScale support team is an important step and can allow them to very, very early make calls, very, very early and validate their designs and design decisions or ideas. So that's how kind of we want to make a simulation of a better use and have more people simulate and have them simulate earlier, as you can see also in this expansion graphic. Good. So how does this in general work? So what's the key points about this, right? So we already mentioned that there is simulation power on demand. So kind of you have the full scalability of the cloud to your usage. That's kind of a clear point and I think easy to understand. But there's also another point to it. So having something accessible on a computer does not mean that it's really accessible to you to use it, right? So there might be operational overhead. You need to involve your IT department. You might have the hardware resources limited in a queue. So there's just different hurdles that you might face when you start using simulation that we can overcome by being a cloud native platform that is always scalable and also helps you every time you face a problem or you have a question, essentially. We call this our in-product support. So we have a proactive support available. You're not trying to add a ticket to some ticketing system and you get emails when the ticket is picked up or is in progress or resolved. You directly interact with our support team on the platform if there's any question or support request that you have. That makes it also easier if you use SimScale in a larger organization to every time onboard new users or expand the usage of SimScale for different teams, because the onboarding can be done at any time, or at least we can support it at any time with your team members. Good. And last but not least, we're obviously spending a lot of time essentially making workflows intuitive and easy, which is also part of why we're showing you today this webinar, as CAD simplification and preparation is just a big pain point in many workflows. And we will show later also why this specifically holds true for electronics and how we want to overcome it and how we can help you with that. Good. That being said, addressing the accessibility first, we want to go now a bit into detail about electronics design. How does the industry look like? What are the challenges? And why is simulation not yet used to the extent it should be used, to later on give you some insights on the solution. So the industry landscape is quite clear. There's a lot of fast-growing industry segments with huge growth potential in electronics, be it high-tech, be it consumer, sensor technology. All of these are really rapid-growing industries, but there's another level to it that in also more traditional industries, automotive, energy supply, etc., electronics components now become essential to core innovation. So like for smart grids, for autonomous driving, all of these technologies require sensors to measure or optimize performance, require a lot of electrical components that need to be added to the mix. So essentially electronics are just expanding into all industries, and that means that also all of these products, all of these devices need to be considered, need to be optimized, and in many cases that is also in regards, or mainly in regards to thermal management of these components. As I mentioned, electronics components are very important to these industries, and that there's a huge growth potential. Every time when there's a huge growth potential, we just see a highly competitive landscape, which comes by nature. Good. A highly competitive landscape leads, in the case of electronics, to very short product life cycles, huge time to market pressure, which you can also see on the graphic on the right hand side, that this is from surveys, the largest pressure essentially on companies, and that essentially if you're not first, you're last, that you need to be very fast to get to the market. At the same time, to really compete with your products afterwards, you need to have high optimization being done during the design process. And some of these objectives, so kind of being fast, but also being better, are kind of opposing objectives, or usually you would require more time to optimize your product. Or if you want to be very fast, you might not get every little bit out of the optimization loop. So if you want to kind of fulfill all of these objectives, you need some groundbreaking technology, or a game changer technology that allows you to still reach all of these objectives by being faster. And that means you need to enable the designers to iterate faster and optimize faster. So the answer to this challenge should be engineering simulation, simply because it has an order of magnitude more design iterations that are possible compared to physical testing. You don't need to do the physical prototyping that already can take weeks, while simulations can be done in hours or sometimes even in minutes. Optimization can be done very early in the design process. Then does not need to be every component already defined to the latest state. You can even do it on subsystem levels, have interfaces to different teams. So you can just start way earlier and already get to a much better optimized product when you consider physical testing, which in the end, obviously, also we recommend to do as a last step, but you're much faster essentially in iterating. And it's also obviously much cheaper. So while you're talking about hundreds or thousands for likely a prototype for a simple even electronics product, you're talking about $10 to $100 likely to simulate such a device. So that means it's just a great match, but still we know that just 1 out of 25 engineers as of today makes use of engineering simulation. And there's reasons to this, and we want to look into these reasons. So what keeps designers from using simulation? At first, we mentioned this, that SimScale is working on making simulation accessible, but in the past or traditionally, it was not accessible as it should be. So software costs are extremely high, installation is required, it requires regular software updates, which means that the IT department needs to be involved. It makes it more complex to roll it out to a larger audience, and obviously it's not very friendly in regards to home office or multi-device usage. So that's in general just a problem and keeps people from using simulation. There's another end, or kind of to the accessibility topic. Access to simulation without productivity loss is really hard to pull off. So that means if you're working on your computer, the simulation has kind of high memory requirements. So that means you either need multiple computers or a cluster, or you will already lose productivity essentially because your system is under heavy load. There might be simulations or other programs crashing. It takes longer. All of this becomes a hassle, and you don't even want to start the simulation at first. So that is something that is required. It also requires quite some onboarding time to get used and started. You need to walk through the user manual, get familiar with the tool. You might not have somebody who can help you if maybe you're just starting using simulation in the company and you're the first to go for it. So that also requires time from you, and time means productivity loss on your end. And usually if you're an electronics designer, you have a lot of other things to pull off and do at the same time. So yeah, as mentioned here, you also might have long turnaround times if you're running on small machines. So if you're running it maybe on a 4-core computer, or you might have long waiting queues because companies try to really make the best use out of their hardware. So that means that to have the level of usage quite high, there needs to be some waiting queues, at least at spikes of demand of simulation. Good. That's not all. Accessibility is not the only thing that keeps people from using simulation. There's also in electronics designs a technological barrier. And that means you're requiring a robust solution. It takes quite some time to prepare or simplify a CAD model so that it's really usable in simulation. If you don't do it, you might run into troubles, into errors. You might spend quite some time tracing those errors down. That might be related to bad mesh. You might have problems converging then your simulation, and in the end, you're not even sure if you will get a simulation working. So you need to make the call at the beginning. Is it worth my time investment to get this additional knowledge, or am I going kind of with just judging by expertise, or maybe I'm not even going for the highest little optimization bit, but just saying, okay, this should be essentially good enough, add some safety factor and give this to physical testing and try to get it to the market as soon as possible. Obviously, then you're leaving out optimization potential, and that shouldn't be the case. So those are reasons essentially why simulation is not used as it should be. Some of them business reasons, like purchasing a software package. Others are rather productivity reasons, so where the end user, the designer, might consider not even starting, or might really think twice before running a simulation or going down that route. We mentioned already, Josef in the beginning and me, that accessibility is covered by SimScale and how we do that. So that shouldn't be a problem. But today's session really is about this little piece here. So how can we make the technology ready and usable so that all of these problems essentially are covered by one platform? And that's what we try to achieve. And we invite you to test it out yourself. Good. So our solution to this is a new solver, an immersed boundary method solver that tries to take care of this by being very robust and resilient to geometrical detail. And talking about geometrical detail, we'll quickly look at why are electronics models really challenging for simulation. So the reason for it is quite clear. We usually have huge assemblies consisting of sometimes hundreds, if not even thousands of parts. We can see here on the right already quite some complex model. Usually these models are also composed from different sources and different people working on it. So you might download, for example, an LED chip or a resistor from a manufacturer's homepage. You might get the PCB layout and critical components from your electrical engineer, and you're working yourself on the casing of the device. So there's multiple things that kind of get combined. In CAD, that's always in some sense a challenge. You have conversions involved, different tools. So that's a challenge, obviously. Additionally, we have topological and geometrical details. You can see also here on the right, there's some logos imprinted. There might be little detailed components like screws with threads, etc. So that's just natural to it. And often we also have overlaps and gaps due to manufacturing tolerances, or maybe the assembly was not well done, and there's there was some difficulties in putting it together, and now there's little gaps that kind of have the enclosure not really closed, but still open. Good. The consequence for designers is essentially that some of these geometrical and topological details are really challenging to mesh. And even if you get them meshed, they are often not really significant for the thermal behavior of the system. So it still hurts to spend a lot of mesh cells that in the end relate to resources or computation resources and time on these components that are not important at all. If you want to overcome that or avoid that, you can obviously clean up or simplify your model, but usually the time of the user is much more valuable than time that is used for simulation. So likely that's not a good option, but with many solutions, it's the only option that you really have. And then, as shown here, simulation turnaround times are still significant to the design process. So we're talking sometimes about many hours or even days. So if you have a question or that needs an answer fast, then simulation turnaround times still play a significant role, and you might need to consider if you're even going down that route as mentioned before. So that's a problem. And if you're going fast and if you iterate a lot, you might have components changing, and you might need to do some of this CAD preparation and simplification work over and over again, which makes it even more cumbersome. Good. So kind of just highlighting the problem so far, let's also look now into the solution and what SimScale is trying to do here. And that's why we are really, really happy that we have an expert today in this call. So our CFD lead, Vuko. So instead of now showing you how this is done or kind of reading through these bullet points, it makes much more sense from us to get him involved and give you some first-hand insights on what we did here, how we tackled this, the problem, and what our solution looks like. So maybe Vuko, if you don't mind, it would be great if you could give us maybe some overview of what the immersed boundary method even is. How does it work? How did we adapt it, and how did we use it essentially to be a good solution for these thermal challenges?
Sure, Alex. Thanks for a kind introduction. Hi, everybody. So, Alex, I suggest that I give you kind of a top-level overview, because you are probably the one who knows that I can talk about these things for hours. And yeah, you just, if you want me to expand on certain topic, you just ask. I hope that works. So,
great.
So how does the immersed boundary method work from the top level? If I had to describe it in one sentence, it would be that a tessellated model, CAD model, is immersed in a perfect background grid. Now, let me expand on these 2 points. So first critical word is the tessellated. So the only requirement we have for a CAD part is for it to be for us to make it possible to tessellate. So if you have an assembly of 50 parts, the only requirement is we have to be able to tessellate it, which is much lower requirement than all the other CAD operations that you might use, you might need if you have a body fitted grid. Now, once we get the tessellated parts, we create a background mesh, which is, as you can see on this picture, it's essentially just boxes or hexahedrons. Why is this important? Because at the bottom of the crux of the solver, it's still the standard finite volume discretization. And finite volume discretization really likes hexahedral mesh elements from the mesh quality and stability point of view. So what we do is that essentially we resolve these contacts between different parts on the mesh level instead of a CAD level. So essentially all the geometrical details that you might not care about from the thermal management point of view can be just automatically defeatured. And we modify the discretization in such a way that we say, okay, if you have, let's say, a heatsink on top of a power source, these are naturally 2 different materials. They have 2 different conductivities. And we kind of enforce these discontinuities on the solver level inside the discretization. So that would be, a kind of a 1 minute, 2 minute explanation. And now, Alex, if you want to dig deeper a bit on something, please let me know.
Sounds great. Thanks, Vuko, already for that. Maybe you could quickly highlight what we understand from this is that the user does not need to do any flow domain or interface treatment himself, right? So essentially all of this is then covered by the solver and does not even appear in the UI. Is that correct?
Yeah, it's correct. So we don't do any kind of flow volume definition on the CAD level. We do it on the mesh level. Just let me give you an example. For external flows, the one that you see on the right, it's just a natural convection problem. So we literally just create a geometry. The user has to create a geometry primitive box, so just a box. And once we mesh it, as you can see also on the figure, we refine aggressively towards the area of interest, towards the interfaces, essentially. So the contacts between the parts and the parts themselves. And once we have this mesh structure, we essentially define the flow volume on the mesh level. And why is this important? Because mesh is by definition closed, so you don't have any problems with leakage. Plus the tolerance is the tolerance is not so strict as on the CAD level, right? Because on the mesh level, you need the tolerance which is essentially linked to your desired fineness of the mesh.
Great. Thanks for these insights. When I think back, Vuko, I remember that we had kind of the discussion we're now presenting to the audience a few months back, and I also remember when I kind of tried to explain really the ins and outs and problems of these complex CAD models, and you drafting the solution. That I asked you kind of is there a drawback? Where's kind of the catch, right? And your answer was there is no free lunch. So I think that's also important for our users. What does it mean, right? Maybe you could also give us some insights on why does it work so well, but also what does that mean for the solution? Are there any drawbacks, or is there any things that need to be considered that we have also the kind of expectation handled well on that? That would be great as well.
Sure, of course. So as you said, there's no such thing as free lunch, which essentially means, in engineering generally, so also here, there's always trade-offs, right? And with this immersed boundary approach, what we cannot do well is we don't have a physical boundary layer mesh, right? Usually, if you do the body fitted approach, you would create the boundary layers, inflate them, and then create the volume mesh further on. And this gives you a very nice possibility to capture accurately boundary layer physics with the standard turbulence models. In this case, you cannot do that because you don't generally know how your surface will cut your background mesh. So you will have some kind of, let's say, irregularities when it comes to boundary layer treatment, compared to, of course, the body fitted mesh. Still, the good thing is that even if you are interested in resolving boundary layer physics in a better way, you can just use more refinement, and with more refinement, you should be able to go to a more detailed level.
Thank you. Great. Great to hear that. I think that's also important, I guess, for every electronics designer, right? Because there might be use cases where the detailed flow is extremely useful and helpful. And obviously, SimScale continues to offer this to our users to run with the body-fitted mesh, physical boundary layers. But the main interest usually should be the critical components, failure of it, or degrading performance based on high temperatures. So the main interest definitely is on that. And we mentioned beforehand that the unlimited computing resources should allow you to go really into detail. So that's also why, from our perspective, this really still is a perfect match for fast electronics design. And that's why we are so happy to have the solution around. Vuko, while we have the pleasure to have you in this call today, would it be possible that you give us a little bit of an insight? We will introduce a bit later that there will be a private beta where people can test this, the external natural convection cases, but also what are we working on? What will be the next steps, and where do we want to bring the solution over the next couple of months?
Sure. So at the moment, I think we, as you said, the beta version will cover the external flow. And at the moment, we are working on a beta release for an internal flow. It's slightly different procedure, which makes things a bit complicated on our end, but nothing that we cannot do. So, and once the internal flow is released, we'll have to kind of work together to define the kind of unified process to be able to handle in the same framework both in internal and external flows. And then I think we're kind of done with the, let's say, heavy lifting. And it will be just of course, with under quotation marks, essentially working on missing features to bridge the gap with our standard conjugate heat transfer offering and the IBM solver. The good thing, though, is that in the background, let's say the number crunching part of the software, though, so the CFD software actually is ready automatically for these features. So we just need to, it will be less work than, for example, handling of internal flow and the things we did so far. So that makes me optimistic.
Awesome. That's great to hear. Also because we know today we don't have only kind of new users that are interested in learning what SimScale is about, right? But specifically, we have a lot of users that have been using SimScale over a long time, also that might have struggled with some of the problems and challenges we mentioned. So I guess they are eager to see this happening and see these features come up. Great. Thank you, Vuko. Thanks a lot for giving these insights. I think also for everybody in the webinar, you know already you can ask questions. Vuko will be around. I guess he's by far the most interesting person in this webinar to be asked questions by you. So if you have any things that come up to mind or you require additional information, feel free to add a question. Great. So then, now we talked a lot about the theory. We want to get a bit into a practical example. So we will show you a demo project on the platform, but also kind of the insights of it up front. We chose here an LED chip on board, LED chip on board light that you can see here as a result plot already on the right-hand side. And we look into the CAD model to see what we have here. This is obviously, as a lighting fixture, not the most complex electronics assembly. So we have only 34 solid bodies in this original production version of the light. As you can see, there is a aluminum heatsink. There's the LED COP chip. We have here the reflector. We have the different casing components, most of this being made of aluminum. But you can also see, I put it here like we have over 20 tiny bodies, not really relevant to the thermal behavior of the system. Many of those also need to be kind of mounted in here, so we have a lot of holes. And obviously what you can also see are that inside of this reflector, we have a lot of tiny little surfaces that kind of break it into little pieces, make it look really nice in reality, and make it horrible for simulation, or topologically speaking, it's hard to resolve this in the mesh. So that's why we did the exercise to simplify and prepare this model for simulation already quite some time ago. And we came up with a highly reduced version where we have only 8 solid bodies left. Some things merged. You see that many of the tiny little components are just gone and were replaced, and the holes were filled. And we removed overlaps essentially in the part which in the original model we still have tiny overlaps in the model that are then again treated by the solver, but we'll see that in a second. Good. Some insights to the discretization, because that's kind of the part that often fails or is problematic with detailed CAD. So that's why let's look into the body-fitted meshes for this use case. We can see here already from the screenshots on the right-hand side, we have a quite high portion of mesh cells required to resolve these topological and geometrical details of mainly these tiny components. Now, you could say then, yeah, just coarsen them up with mesh settings, but you then might run into the problem that you have really bad mesh quality, and simulations might be failing or slow converging. So there is not really a good trade-off that you can make. You can also see that even for this model, for the simplified model, we had over 10 million cells already for the first trial. So with our default settings that are meant to be rather a coarse and first shot at the simulation, for the very detailed model that you can see here, it was over 20 million cells for the first mesh created. You can also see from that 10 to 20 million, we have roughly a factor of 2 between the mesh size of the highly simplified model and the original model. So a big difference. So the time investment you spend into preparing and simplifying at least pays off in regards to mesh size. If that's worth your time, we let you judge based on what's still up to come, right? So for the Cartesian meshes now, this is different, right? So you can adjust the meshes from very coarse to very fine with no problem. You can start very, very low on the fineness scale, and you can go very high. There's no significant difference for these meshes between the original and the simplified model. So in our case, that was max 3%. So the original model has a bit more cells because we're trying to refine towards the details of the model, but there is no big difference. We will also see that in simulation turnaround times later on. Yeah, and as I mentioned, you can go really far down as you kind of want to, but reasonable results you can already cover with sometimes simulations around 100K cells. So for example, for our lighting fixture, we already get in a good range of what we expect then from the finer resolution runs as well. So plotting this in a chart and giving these insights again, you can see here on the x-axis we have the different coarseness level that SimScale gives you as kind of a default option to meshing, so scaling from very coarse to fine. And we have on the left-hand side the mesh size in million cells. So you can see in red we have the a simplified and original model for the body-fitted approach. And you can already see for the coarse mesh, we have here around 10 million for the simplified model, and we have 21 million for the fine model. We don't have even a mesh in very coarse, because we cannot even create it on a level where the simulation would still work. And we don't have one for medium and fine, because we don't really want to go for this setup, for this model, on a higher mesh resolution level, so to 50 or 40 million cells. It does not really make sense and doesn't pay off. So we're kind of stuck within one step or one refinement level. Opposed to this, with the IBM meshing, or kind of the Cartesian preparation, we have here really, we can use all levels of refinements. We can obviously also adjust them, but we start from around 100,000 cells and go for fine meshes up to around 10 million, meaning that we start with the body-fitted meshes with our first simulation, where we end up now on the fine level with the Cartesian meshes. Obviously, we can go even further, but I think gives an impression of what you can already do up front and how you can be much faster by running some coarse and rough simulations early compared to this very detailed and high-level mesh. And you can also see that the difference between the original and simplified model mesh is really little, right? So I mentioned it's below 3%, so the mesh sizes are almost the same, while for the body-fitted meshes, it almost was double. Good, then let's look at simulation, convergence, and runtime. We start with the simplified model. Why do we start with the simplified model? Because we couldn't even run the complex model mesh. The 21 million mesh failed. So we start with the simplified model to give a comparison between the IBM results and the body-fitted CHT results. What you can see here is all the blue lines are the convergence plot, based on iterations, the temperature of the chip for the IBM solution, and you have in red the body-fitted solution. So the body-fitted solution goes a little bit further because it was not fully converged, or at least we couldn't judge at that point at 1,000 iterations, while the IBM solution was already fully done. So that's why this extends a bit. But what you can see here is that the max difference between coarsest and finest runs from all of these simulations was max 6% difference. You can also see from the very dark blue line that for the very fine solutions, we are really kind of on an identical level, or very low difference in solution level. We have here roughly 30 degrees temperature increase, so that's kind of our base for judging the percentage value. At the same time, people are usually not that much interested in iterations because it's just a numerical term. We are interested in CPU time. So how much simulation time do we need to run this? And obviously we keep in mind that with SimScale, we can scale up to 96 cores. So we can even cut down the simulation time by using bigger instances, but it should allow us to compare quite well how the simulations for IBM and body-fitted CHT compare. And what you can see here is, or what you might not even be capable of seeing is, right, the first result is already done after 3 minutes and 0.8 core hours. So that's the coarsest, the very coarse simulation setup with IBM, and it's kind of so fast that we cannot even resolve it here in this chart. And for the finer solutions, obviously at some point we get in the same range as we have with body-fitted, but at that point we could already run coarser simulations and have feedback and yeah, as you can see on the left-hand side, reasonable results already. Having a similar look at the original model now, what I did here is plot essentially again our simplified model for the body-fitted CHT, because we don't have here a simulation result on the original model, but also plot the results for the simplified and original model on the coarsest level, which is a bit above 100K cells. And what you can see here is that we have a smaller difference than 3% between the original and the simplified model simulations. Meaning, in this model, as it was also in some sense quite well prepared in the original state, not too many gaps and overlaps, we really get absolutely comparable results if you're running the simplified original model. But you need to kind of keep in mind that 30 minutes of CAD preparation work were invested into the simplified model of a human being, in this case me, which you could just save and assume you're not having a lighting fixture but a complex electronics enclosure, some control unit or similar. This scales up with the complexity of the model. So you might spend multiple hours that you can save by using the original model and using the new technology to run this. On the right-hand side, you can again see kind of the runtimes. As I only plotted the very coarse solutions, we can again not really even see this. So let's pull it out and only look at kind of the lower level CPU times. And we see that kind of both simulations are down below 1 CPU hour, right? So if you're running this on 16 cores, we're talking about 3 to 5 minutes for the first result. Good. That's what I wanted to show you up front as a to look into the results. I would now give you some insights on the product. How does it look like? How does the setup look like? How does it compare to our current solution? Yeah, and how do the results look like as well? Good. So let's first look at the original model that I showed you in the presentation. Now on SimScale, you can see here we're now on the platform. This is my user profile, and I opened simply the workbench. You can see I have here multiple geometries. The simplified model. I have the simplified model also with a flow domain, because we still require the flow domain to run the our current CHT solution. For IBM, we don't need it, so I have these different CAD versions in this project. Let's at first maybe just quickly take a look at what I showed you about these refinement settings. So here you can see that we define simply for these Cartesian cells, we define a number of cells that will be put in each direction. And down here we have this refinement level, which I was relating to as coarse, very coarse, fine, etc. So our very coarse solution is a number of refinement levels, in this case 3. I'm right now saving this, and let's kick off a run so that we can see how this progresses. Good. After this was done, you can see that obviously I prepared the runs already up front. I'll show you quickly how the setup is done. So as usual, I'm assigning simply a geometry. Now in our case, I do not add the flow region. I'll just add the model. You can also see on the right-hand side already that we have these 34 components. They have all the manufacturing names. This is really how we brought the model in. In this case, this was a step file. We prefer native formats, but you cannot always pick or choose. In this case, it was assembled from different sources, so it was exported as a step file in the end. What is now important is we add materials as before. There's no big difference to this, but there's one difference. We do not assign now the flow domain in this setup to a region. So we did not do a flow volume extraction up front, but we just added here a geometry primitive named in this case flow domain, was done here. Just a bit extended in Z direction, as we have here gravity acting, and then assigned to the air. So that's what Vuko talked about, that there is no kind of physical flow domain or a CAD solid body that represents the flow domain, but we're just putting essentially a primitive around it, and we resolve everything later on during meshing or solving. Good. Apart from that, the setup is very comparable and similar to what you know. So you've seen now materials. You might be missing the boundary condition setup. The reason for this is that currently This prototype is meant to be external natural convection cases only. Vuko mentioned that we're working on an internal prototype as well that will then contain all the boundary conditions. But for an external natural convection case, essentially all you need is a box. And as all boundary conditions then are open environment boundary conditions, so usually on our platform called natural convection inlet outlet, we did not even add it here. It's just assumed for all faces of the enclosing box. Good. Apart from this, again, we can add here power sources. In this case, this lighting device is usually running on 450 milliampere, I think, adding up with the voltage of, I think, 31.4 watt to 11.5 watt power. So that's what we put in here. No, it's 15 watt power, but we have 75% of the power being dissipated as heat. 25% is optical performance. So that leaves us with 11.5 watt, and that's our load. And I put here some result controls in. For example, let's look into the assembly. We have a probe point in here placed directly in the LED so that we get the temperature from the COB chip. Good. That's about the setup. That's everything you need to do. There is no CAD preparation or anything like this needed, but if you want to run it in our current CHT and you don't want to run into troubles, I've shown this here. So I mentioned that the course simulation for the original model without simplification actually fails. It is working if I prepare the model a little bit. So if I, as mentioned, simplify the model, I can run the simulation. We mentioned the mesh is 9.7 million. We also have here a flow domain added now. So you see the solid body of the flow domain in a second coming in. And now obviously kind of hiding this, we have the simplified model. So many of the components missing. We can also look into the interior. We'll see that the reflector does not have all of these little details. That's important. Otherwise, as mentioned, the mesh goes to 20 million or is not even possible to create. So as I did this, and as we want to show the difference between the two solutions, it also makes sense to quickly look into the into our CAD mode to show what was done to do this. But before I do this, we want to at least notice that our simulation in this moment finished. So after a few minutes, we now have the results ready to look into the IBM results. I'll still quickly show you what was done in CAD mode. So while loading this, you know that SimScale is not a design tool. Our CAD mode is purely designed to help you prepare and simplify models if you want to. Even for a solution like now our IBM solution, it might be beneficial that you spend 3 minutes of your time deleting just completely irrelevant parts. We give you the selection methods that you should require to have fast access to these things. But let's look now what was done in this for the simplified model. So what you can see here, I started essentially deleting just parts on the outside, deleting faces, unioning essentially parts that are should be connected and should not be resolved separately in the mesh. I subtracted over here the parts to resolve the overlaps, and in the end essentially just created this external flow volume. Good. If I select in here in the tree one of these operations, we can also look at how it looked at that point and what was done, right? So as mentioned here, I just deleted a couple of small components, and right after that then deleted also the faces of these, for example, small screw holes that were in the model. Good. Let's exit the CAD mode again and look at our results, which will kind of be the end of this little demo. And then I'll explain how this can be accessible by you, because that's likely much more interesting for you than watching me simulate the model. Good. We ran the original model in IBM. So we'll expand the simulation tree. We have now our run 5. We'll quickly click on it. Took 4 minutes, 8 core hours, was probably run on 16 cores in this case. And we open up the solution fields and can see here now the simulation results. So in this case, by default, it shows me pressure. I'm really interested in temperature. I also want to see the mesh in this case. So let's also show this. And now, yeah, we can see, right? So we ran the core system level. You remember the details of the model. So this is really a coarse representation. I showed you in the slides also cut sections of the moderate and fine solution, where really every little detail is then resolved. But you also see that you can go as coarse as you want, essentially, and still then run the simulation and get, dependent on the complexity of the model, good results out of this. Good. That would be the quick live demo, and I'll jump back to the slides. Good. As mentioned before, what we want to have right now is potentially the audience of the webinar or our users making use of this solution, getting back to us. It's in a very early stage of development, but as we also mentioned, we are quite far progressed. We think in the next couple of months, we can have the solution be on feature parity with what we are offering for the CHT solver. But we want to now get your feedback on how well this is working. We want to see how it behaves on your models and work with you collaboratively on improving the solution. That's why we decided to have an early access program on this. So a private beta for the external flow, and likely shortly after also for the internal flow prototype. How this will work is at the first point, simply reach out to me. My contact is available here. So you reach me under rfischer@simscale.com if you really want to have access. We will schedule a kickoff session with every tester. So first to give insights on it, but also to understand what problem the tester is trying to solve, right? And be from that point on in close contact with you to really make sure we get the feedback out of these testing sessions and testing periods. So that's how we will approach it. If you overall got interested in SimScale and you would love to see a more detailed demo or maybe a discussion about your application and also how this works out business-wise, you're also welcome to always reach out to our sales team. What happens usually is within a day or two, somebody will contact you and see if there can be a call arranged with one of our support engineers also to give you some technical insights and discuss your application. Great. That being said, we reached the end of our webinar, so I'll hand over to Yusuf. I thank everybody kind of for the attention, and specifically also thanks Vuko for covering the heavy part or the really interesting part about the technical details and kind of backing me up on that.
Yeah, thank you so much, Alex and Vuko, for the great presentation. And with that being said, we will now kick off the 15-minute Q&A session. So if you have any questions regarding our new IBM technology, SimScale in general, or the presentation, or even the simulation and demo from Alex, make sure to ask your question, and we'll take them one by one now. Excellent. So we'll go through the questions now one by one. Thank you again, Alex and Vuko. And I guess we can jump straight to question number one, which is how does this work with the Revit models? Does it remove the smaller details in complex models? I think that's that one that you could take, Alex.
Yeah, so Vuko mentioned that we are already working on a prototype for internal flows, right? So if you're talking about Revit models, I would expect that the reason for this is likely HVAC simulations. Usually Revit is only used in for building modeling and used a lot for that purpose. So I would expect likely that this is not a natural convection case around a room, but it's really an internal flow HVAC study. So we are working already on a prototype to enable this, and then it will be also well suited for these kind of applications. The requirements are very similar to what we mentioned for electronics models, where usually we rather see a SolidWorks Creo or CATIA files that come in. We essentially just need that tessellated surface, right? So as long as we get a model consisting of solid bodies, the solver can essentially handle it. So also for the AEC world, where CAD is also very complex, sometimes even dirty, the solver is well suited and will potentially be also a use case next to electronics cooling.
Excellent answer, Alex. Thank you so much. I think we have one question coming in for Vuko. What happens if there are small gaps in the model? Does the volume get closed up by the solver, or does it simulate an open domain in that case? Quite interesting.
Okay, that's a good one. So if your gap is smaller than the local cell size, then it will be closed up. Just to give you an example. So if you have a gap of 1 millimeter and your local cell size in the area of the gap is, I don't know, 3 millimeters, then it will be considered closed. On the other hand, if you have, let's say, a couple of cells across the gap, right? Then unfortunately, we cannot help you there. It will leak out. So essentially, if your gap is 1 millimeter and your cells, you have cells of 0.2 millimeters across the gap, so let's say 5 cells, then it will leak out. It will be considered as a fluid domain.
Mm-hmm. Excellent. Is there anything you would like to add to that, Alex, or does it cover the question?
Yeah, I think that's really what is required for this. Maybe what we can add is that we want to still support with our CAD mode, right? The preparation that sometimes might be beneficial. So also for that reason, it makes sense to highlight where gaps are, and we're working on an implementation to also make this available so that you can upfront see, are there any gaps in the model? Could you potentially, as I highlighted, the little difference between the results of the original model and the simplified model, there seemed to be no bigger topic, right? Though that there's essentially a gap that makes a big difference for the cooling performance, but it could be in a model that there is something that really influences the thermal behavior, and then it's important that you understand this and that you can see it. So to identify those, we are working also on operations to highlight this.
Great, thanks, Alex and Vuko. And we have another interesting question coming in, which is external and internal flow was mentioned. Is there a plan for enabling a combination of, for example, liquid cooled systems where natural convection plays a role? Alex, I think that's for you.
Yeah, so I think this is roadmap related, so makes sense that I cover it. Again, I'm kind of referring to what Vuko said. While developing now this solution, the team kept in mind where we are heading, right, and prepared it nicely so that we can now execute on reaching feature parity with what we already have in our offering, but also to extend it further. And that also refers to running multiple fluids. So right now with the external solver, you will only have essentially the box. So the most common use case, or potentially only use case, will be that you have an air enclosure. When we enable the internal prototype, you will also have the possibility then to run internal flows, water cooled or different cooling liquids, but directly after we will also then extend the functionality that this becomes kind of a general purpose again thermal solver, and you just decide essentially which mechanisms of heat transfer you put in. So if you have then an internal flow like a cooling plate, but around the assembly, natural convection is considered to also play a role, or you're not sure if it plays a role. That's kind of why simulation is so helpful, right? If you start a physical test, you also don't know the answer up front. You're hoping, or you have a hypothesis that the design should cover what you expected. It's similar with simulation. So kind of the safe route would be to consider all mechanisms. So natural convection, liquid cooling, the potentially also thermal radiation, and then it doesn't play a role anymore. There won't be an internal and external solver. This will be just one IBM solution that you can use and do all of these sorts of simulations.
Perfect, Alex. That was a very nice answer. I think with that we can wrap it up, and we have -3 minutes left for this webinar, so I encourage you to check out more webinars under simscale.com/webinars-workshops, or feel free to scan this QR code to be updated with the latest webinars that we are offering, especially for electronics cooling and further product updates. Thank you so much for attending. Also, big thank you to Vuko and Alex for covering a lot of questions and also for the nice presentations. And I guess I'll see you in the next webinar. Bye-bye.
Bye.
Bye.